All right, how's it going, everybody? We are here on Friday, March 5th. Today we're going to be talking about section 8.2, area of surface of a revolution, right? So surface area, but particularly of surfaces of revolution. Before I start, I have more words above my head than I normally do, so I just want to talk through some things real quick. We're hitting section 8.2 today. This is our second video associated with week 8. Week 8 is the week immediately before spring break here. I'm looking at my calendar right now. So week 8 is our March 8th through March 12th. That's the Monday through Friday. March 15th through 19th is spring break. March 22nd through 26th, that's the week immediately after spring break. It looks like, since I'm making these videos now, much to my wife's dismay, she still has a baby inside of her. While both of us were thoroughly expecting this to be a little bit sooner, it looks like my wife is sticking it out a little bit later here than we anticipated, or I should say, my daughter is sticking it out later than we anticipated. So, what it looks like is that our canceled, hardcore air quotes right there, week is going to be the week after spring break. It's not that there's no class, it's just that there's no new content, right? So the week after spring break is baby week, meaning the only thing you're going to do that week is take a midterm. So again, as we get a little bit closer to that, and as I write that midterm, I will send a message to you guys first, an announcement in Canvas that will tell you when you should expect it to be available, and then it'll be posted in Canvas, and you'll all have, I haven't quite decided the technical details of this yet, but something like 48 or 72 hours to complete that midterm. That will be your only obligation for the week immediately following spring break. The week then after that is going to be, so spring break was 15th through 19th. Midterm slash baby week is the 22nd through the 26th. Again, that's a Monday to Friday. So then Monday, March 29th will be our next covering a section of this course day, which will be section 8.3. We'll get our another little physics section here. Our kind of wrap up here in chapter 8 is that we're going to get a physics section in 8.3. We're going to get a probability section in 8.5. And I think that's all that we cover in chapter 8. As I have alluded to many times this semester, we do have a sort of not to be scary, but a one remaining monster unit of this course, which is chapter 11. But there is one little thing that we stick in here before we get to chapter 11. Remember that we skipped chapter 9, which is on differential equations, because that's a whole course that you're all going to take next year. But chapter 10 is where we hit a couple things like parametric curves and polar curves. And we want to do a little bit of calculus with parametrically defined equations and with polar equations out there. So chapter 10 is kind of cool because it really just goes and revisits everything we did in chapter 7 and 8 and says, well, how would you do this if we were in polar? How would you do this if we had parametric equations x of t and y of t instead of y being a function of x? And so it's really just a revisiting of topics that we've already seen, but saying, how would we do that if we were in this different coordinate space here? So we really just hit, I think, 3 or 4 sections of chapter 10. I'm doing my super quick review. I think it's 4 sections total in chapter 10 here, but those aren't too crazy. First 4 sections of chapter 10, and that's when we hit chapter 11. Chapter 11 is a pretty big diversion from things that we've been doing. We're going to spend most all of chapter 11 talking about sums rather than integrals, but they are very, very closely related since an integral is a limited sum. So they are very closely related. We'll see some nice interrelation there, but that'll be kind of our wrap up this semester. That chapter 11 topic there. So that's kind of our stuff coming up right now. Is that this is we're at the halfway point in the semester. You know, we're week 8 right now, and there is sort of a double break in that we get 1 week for spring break, 1 week of no content, but just a midterm while I take a little breather with the baby, and then we'll be back in section 8.3 at the last week of March there. So. Section 8.2. You guys have already seen the 8.1 video, and I don't want to say it's easy because there's some hard integrals that can come up right there, but conceptually, I think it is a pretty easy idea for our arc length stuff. It's literally just take the integral of the distance formula, and that's all that's really happening right here. We're going to see that our surface area formula is very closely related to that. The formula is going to look a little bit grosser, but it's not really that bad. Again, it's going to come up with some integrals that might be kind of tough. It's going to come up with some integrals that are probably going to lead us to a lot more trig substitutions once again. But conceptually to build the formula associated with surface area here is again going to be something that I think follows very naturally from just some simple geometry ideas. After we hit a few examples associated with surface area here, this is our last like geometry section of this semester, which we've done a lot of really difficult geometry this semester. And so I want to kind of conclude all of our geometry discussion with some kind of like very like this isn't like some particular calculus application, but more of like a super broad theme of how calculus relates to geometry. So I'm going to kind of show you guys some cool stuff I never want to think of anything in math as a trick, let alone a magic trick. This to me is like as close as we get to there being a magic trick, but it's really just a description of a deep relationship between derivatives and integrals. So that's what I'll conclude with here today. Okay, there's my 7-minute intro right there. Let's go ahead and start this guy. So surface area. We're just going to see a diagram. We're going to see some geometry. We're going to find the area of a geometric shape, and we're going to integrate it. It's going to kind of be pretty direct relative to what we've done with things in the past here. So here's our diagram that I found on the internet. It's going to help us visualize the geometry associated with what we want to be doing. A Riemann idea here is going to say, let's go ahead and subdivide a curve in this very low resolution image right here. There's a red curve. So we're going to subdivide the curve into n subintervals. That's something that you've done in like 12 different contexts by now in your calculus career. Decompose that curve into n straight line sections, just like we did with arc length in the previous video. And then estimate the area of each of these green bands. We're going to estimate it as the surface area of a cylinder. Right now, this looks a little bit like a cone, but what you can imagine is that as our delta x gets infinitely narrow, the area of that cone slice, also known as, by the way, it's called a frustum. When you take a cone but chop off the top, that's a really weird name, frustum. But in any event, we're going to estimate the area of this cone slice as a cylinder because it will get infinitely close to that as our dx gets infinitely small. And then we're just going to add up the area of each of those bands. So all that we're going to get is just the integral of band area. That's it right there. We're going to add up the area of a bunch of these bands, interpreting them as cylinders because their surface areas will be infinitely close to that of a cylinder's area once the delta x becomes dx and gets infinitely small. It's pretty straightforward here, kind of geometrically speaking. Slice it up into bands, add up the bands. So let's go ahead and derive this formula for surface area. And the reason I put deriving in quotes right there is because probably want a little bit further justification if you really want to go into like the depths of this formula right here to convince yourself that this is going to be well approximated as a slice of a cylinder rather than the slice of a cone. But that is something that is available to be shown to you if you wish to kind of pursue this slightly deeper right here. So that's why I put that guy in quotes right there. But we're still just going to like build this formula naturally by geometry right here. So here's what I'm thinking. Let word integrals be our guide here. Our surface area, all we're going to do is add up a lot of bands. All right, so that's what I mean. When I say a band, again, I mean like a strip around this thing. One band of it. I don't know. I'm using a word right there that's not very technically defined, but one strip, a thin slice around our surface of revolution right there. So what we need to know is what is the area of one band? And as I do, I go way overboard with my use of the word Riemann right here. But again, as I've emphasized it dozens of times this semester, when I refer to something as a Riemann blank, I'm saying it is a representative object of which I plan to add up an infinite number of to accrue some meaningful value to me. So I'm referring to this as a Riemann band. You'll never hear any other mathematician probably say that. But conceptually, I think it's good to stick on that descriptor of a Riemann something to say this is my generic representative object. So what do these bands look like here? Well, if I were to kind of like make one band vertically right here. Yeah, it wasn't too bad right there. Then what we can picture for ourselves, just as we've done in the past with our cylindrical shells, is that we could slice this thing and open it up, right? If we slice it along this line right here, I'm cutting it right there and then opening it up. what we can see is that this right here is going to be our arc length, right? That's our arc length because up here in this picture up above, that's literally what we did. We subdivided into n subintervals and we're getting a length along each one of them. That length from P1 to P2 right here is our estimate of the arc length of the curve right there. So that should exactly be our arc length component that we saw from the previous video. And what we can see right here is what is this length right here, this long length. Well, remember that this is an unrolled like circle right here, or band, I guess I should say. This is just circumference right here. It's the circumference of a circle. Oh, fell off the side right there. That's okay. You can still tell that word is circumference right there. I'm a little funky on my... In fact, I do... Well... Wait a minute. That's kind of strange, actually. How far... Oh, I see why I'm... Okay, whatever. That's fine. Hey, there we go. Now you can see it all. Perfect. So there's our circumference right there. So the point is, the area of one band, if we unwrap the band, it's just a rectangle. So the area of one band is just arc length times circumference. That's it. That's the area of one band right there. We're estimating it to be a slice of a cylinder right there. So it looks like our surface area formula is, when I say it's the adding up the area of the bands, we're really just going to be taking arc length times circumference. Or I'm gonna write it the other way just because the formula is typically written the other way. Whatever. We know that multiplication goes in either order right there. Circumference times arc length. And what are we going to get here for this guy? Well, I know how to compute a circumference. That's 2 pi r. And I know how to compute arc length. That's the square root of 1 plus dy dx squared dx, right? Here we factored out the dx in that context right there. So all we got to decide is what's going on with R right here. You guys became professionals at determining how to measure your R as either an X or a Y, a function of X or a function of Y perhaps, way back in early chapter 6, and we're going to see those same things right here. Really, we're going to write this just as we wrote our arc length formula 2 different ways in the previous video. We'll write our surface area formula just in the X version and the Y version that are equivalent to each other here. So we can get that our surface area is equal to the integral from x equals a to x equals b of 2 times pi times. Now, since we're measuring x here, we're going to do a dx interval, integral. So that means that we're doing y as a function of x, right? That's our radius term right there. And remember that this is like y equals x cubed plus x or something like that, right? So it is an expression of x, but it's what y is equal to in terms of x right there. And then times our square root of 1 plus dy dx squared dx. Or we could say that this is equal to the integral from y equals c to y equals d of 2 pi. Perhaps you have x as a function of y, right? So x equals y cubed minus 1. That would be something that you could use. Y cubed minus 1 is what x is as a function of y. And then we could take our square root here for our arc length form, 1 plus, and this would be dx dy squared dy, right? Because we factored out the dy squared from this guy right there. So those are 2 different formulations depending on whether we're rotating around a vertical or horizontal axis. Again, you're going to have to think your radius thoughts right here, just as you did back in chapter 6. But that's kind of the hardest part about deciding what to do with this formula right here. Once again, you got to recognize that we're getting these square roots of 1 plus a square. You should expect these to lend themselves nicely to trigonometry substitution, stuff like that. You can see this 2 pi isn't ever going to affect your integration, but that every single surface area formula is going to, some way or another, have pi in it, right? Because this 2 pi is going to be a constant multiple associated with all of them. You can see that one little thing that might make these a little bit more challenging than the arc length ones is we don't just straight up have a single square root quantity. We're going to have a whole function times the square root quantity right there, which might make it more difficult for us to be able to actually evaluate the integrals that we're looking at here. So I think, like I kind of said before, I think that doing some of these problems can get to be a little bit more challenging than our arc length because just multiplying by a whole additional function in here makes it less likely that this is going to be integrable by you, right? On the other hand, I think that conceptually this is relatively easy. You just got to remember that we estimate these as bands. The area of one band is arc length times circumference, and so our integral formula is arc length times circumference. There's nothing more to it than that right there. We just took what you knew circumference to be and multiplied it by what you knew arc length to be. That was all that happened. So conceptually easy, in practice might be more challenging right here. So let's go ahead and look at some examples and see that. And I want to remind you guys, because I do like to be consistent with this, anytime you get some new formula, and boy, does this not look like a nice formula right here, a good thing for you to always do, since you are now adult mathematicians, is to say, maybe I should try this against something I already know to verify that I have the right formula and I know how to use it, right? So what's the thing that you think that we should find the surface area of? A three-dimensional shape, a volume of revolution where you already know the answer? Let's go ahead and look at the surface area of a sphere. This is something where we already know the answer to this one, except for the fact that I don't think that most of you know what the surface area of a sphere is. But as I kind of said at the beginning of this video, I'm going to show you at the end of the video how all of you should remember the surface area of a sphere as long as you know the volume of a sphere for the rest of your life here. So this is the one we're going to kind of start with here today, right? Our verification example in a sense right here, our validation, I guess I should say. So what is the surface area of a sphere of radius r? It is 4 pi r squared. And again, while technically that's just sort of a geometry fact, it's certainly in the lesser known category, right? And I guess I expect everybody to know stuff about circles, but it's often the case that most people aren't as familiar with their sphere facts geometrically right there. But 4 pi r squared is the known surface area of a sphere. So again, we'll talk about that one at the end a little bit here. So let's go ahead and figure out how we can come up with this surface area right here. All right, so we're looking for a surface area of a sphere, but we need to be able to interpret this as a volume of revolution. So what's the object that we're revolving around an axis to produce a sphere? A pretty easy question right there, I'm hoping. Just a circle, right? So a sphere of radius r is produced by revolving a circle of radius r about the x or y axis. Or really, literally any axis that there ever could be. Certainly those are our easy ones for us to think about right here. So let's go ahead and and notice, by the way, I can even really just think of this as a semicircle right here because when I revolve it around, I will get the full shape. I don't actually need the top and bottom half. Notice that if you take a full circle, top and bottom half, and do a full revolution, you'll actually kind of sweep out the sphere 2 times, right? Because once you've done 180 degrees of revolution, you actually got the whole thing. If you then did a full 360, you'd get the whole sphere a second time right there. That's an important idea that's going to come up in Calc 3 for all you guys when you do your cylindrical and spherical coordinates right there, that you only need to do 0 to pi as your rotation to get the whole thing if you start with the whole circle. That'll come up in Calc 3. But again, right here, I think that if I just revolve just this guy right here around the x-axis, then I'm going to get that entire shape that we're interested in right there. All right. So I know that this is a circle of radius r. We're doing this generically. Yesterday for our arc length example, we said like a circle of radius 3. Today we're just going to do radius r. Keep this really generic right here. So what I'm thinking to myself is that my surface area should be the integral from negative r to r of 2 pi r square root. I know that I'm doing this as I'm revolving this around the x-axis, so I'm picturing my bands being oriented like this. It looks like my infinitely thin dimension is going to be the dx dimension right there, right? So it looks like I'm going to be doing my 1 plus dy dx squared dx, right? So what this tells me is we need dy dx, right? Right? Those are the two components I need, r and dy dx. So it looks like in this case, we're going to be, since we're measuring from negative r to r, it looks like we're thinking of r as an x-axis measurement right here. So that one's direct right there. It looks like I can just say that r, oh, wait a minute. Ooh, sorry. Where are we measuring the radius of this thing right here? I suppose that what I'm seeing is that the radius of each band, ooh, I better get rid of this right now. The radius of each band, I'm gonna write this out since I just did this wrong. All right, so what you should see here is that when we take this Riemann stick and revolve it around the y-axis, it's going to form a band that is oriented this way, right? Like I'm making a band, but it's oriented this way relative to the way that I've drawn it. The radius of this thing goes from the center, right, up to whatever the y value is going to be. It's a y measurement that we're making right there relative to our look at it flat right here. So be careful with these. I obviously just was like, oh, da, 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 and I kind of, at least I noticed it right there. But stop and think about what geometrically is happening when you do this revolution right there. It looks like the height of our circle is what's measuring the radius of a band in that sense right there, based on the fact that we're rotating around x. It seems therefore that our radius measurement should be a y measurement right there. So let's go ahead and find our dy dx here then. So we know that our area of a circle is going to be x squared plus, or sorry, our formula for a circle, x squared plus y squared equals r squared. We need to know y. It looks like that's going to be the square root of r squared minus x squared. I know you guys have done that type of math a million times in your life by now. Notice, once again, technically speaking, algebraically, this gets a plus or minus right here. I am dropping it because I am only considering the top half of the circle, but it was there, but then I dropped it because I said I only want the plus branch right here. So quite unfortunately, it seems like we need to take the derivative of this guy. Even more unfortunately, it seems like this expression right here is what's going to go in place of r right there because it's y, right? Which is, this integral is going to be a little bit grosser than we had for our arc length ones in the last video here, that's for sure. So then dy dx here, what are we going to get? Well, I'm thinking of this as y equals r squared minus x squared to the 1/2. I need to take the derivative of this with respect to x. So I'm going to get a 1/2 r squared minus x squared to the negative 1/2 times negative 2x by the chain rule right there. In fact, I think we did this exact same derivative yesterday. Our 1/2 and our 2 are going to cancel. This is a 1 over a square root term right here. That x is going to be up in the numerator. So it looks like I'm getting dy dx equals x over square root r squared minus x squared. So it looks like I've got all the terms that I need. I know that r is going to be y. I know that y is the square root of r squared minus x squared, and I know that dy dx is x over the square root of r squared minus x squared. So I have all the components that I need now to build my surface area integral here. So negative r to r. We've really got 2 pi y square root of 1 plus x over square root r squared minus x squared squared dx. So the two things I'm going to do in the next line are substitute in y as my expression of x, right? And by the way, that's all I was writing right here, right? When I said y of x, that means y is a function of x, just like we've got down there. Square root of r squared minus x squared. It's a function of x. So this is y, but it's full of x's, right? Plus a constant r. So it looks like we're getting here the integral from negative r to r of, I'm gonna do three things in this line. I think that this 2 pi r can go sit on the outside now. I don't need to think about that guy. Or sorry, 2 pi can go sit on the outside. So from negative r to r, y is our square root. I don't think I need the fractional power. I can write this as a square root right here. Square root of r squared minus x squared. That's y right there. That's y. It's come down right there. Times the square root of 1 plus x squared over r squared minus x squared, right? Notice x got squared, the square root got squared, and so it went away. So now it looks like I have, well, there's two things I'm kind of thinking here. One, I'm multiplying two square roots by one another, and I am remembering that like the square root of a times the square root of b equals the square root of a times b, right? We can just do that multiplication underneath the square root right there. The other thing that I'm seeing is I find it highly unlikely that I'm just going to be able to leave that 1 to hang out all alone by itself right here. So like some way or another I need to do something. So what my two choices are, I kind of feel like right now are either I could get a common denominator underneath the square root right here, right? R squared minus x squared over r squared minus x squared, add them together, then maybe do some multiplication, or maybe just do the multiplication directly right now. Either way is not too bad algebraically. It's obviously going to lead you to the same place. So I think I'll just do the multiplication version here. So I'm going to get one giant square root here. And it looks like I've got r squared minus x squared times 1 plus x squared over r squared minus x squared. Now, the reason why this looks like a really good idea to me is because it feels like this r squared minus x squared on the denominator is going to cancel with this one that I'm multiplying in here. So it looks like this is a good call because it's going to help me simplify my fraction situation here. And what are we going to get here now? Well, it looks like r squared minus x squared times 1 is r squared minus x squared. Plus, when I multiply this, all it does is cancel the denominator, leaving us with a plus x squared. Ooh, ooh. That worked out super nice. And notice, r is just a constant. R isn't even anything that we're like integrating. That might as well be the number 4 sitting right there, right? That's a constant. I can literally just pull that out in front of the integral. There's nothing to this. Literally that entire integral just like dissolved. This all that gross stuff in here. Holy cow, did that look terrible for us right there? This is literally the number 1 was all that was right there. It was really hidden. So I'm going to integrate this with respect to x, get 2 pi r x evaluated from x equals negative r to x equals positive r. And that's going to give me 2 pi r times x is positive r minus x is negative r. That's 2 pi r times r plus r is 2r. And hey, that's 4 pi r squared. That's pretty sweet right there. That was highly satisfying to me. I know for a fact that that's what the correct answer is already because I know geometry rather than just knowing calculus. I know that the surface area of a circle is going to be 4 pi r squared. It looks like our formula did bring us to that, so I feel pretty good about the usage of this formula now. I don't expect for my integrals to work out this nice in the future right here, but there was some serious thought we had to give into setting this up. I mean, the hardest part of this problem is the part that's on the screen right now, and it seemed difficult and scary. Once we got into actually doing the integration parts, it literally turned into the literal easiest integral that there is. The integral of 1 dx is x. It's not going to get any easier than that. It literally can't. I guess the integral of 0 maybe could be easier, but 1 is the second best number on earth to do math with, right? So as long as we're a little bit careful with our setups, and I mean, what is this, the 1,000th time this semester that I'm going to say to you guys, listen, being able to do the algebra, the geometry, and the trigonometry, that's the hard part. The calculus ends up being the easy part in most of our contexts right here. Being able to think geometrically, don't make the mistake that I tried to very quickly make right there in terms of interpreting your R, and you're going to be good to go with these guys here. So recognizing that your job when you do surface area is saying, I need to know a radius, I need to know a dy dx. And obviously in this case right here, I just told you an object. I didn't even give you a formula, right? So in this case right here, we had to say to ourselves, well, I know this would be revolving a sphere. We had to choose an axis. I kind of arbitrarily chose the x-axis there. I computed my terms that I needed, let the whole thing kind of like fall together right here. So hopefully you find these. I don't know. I always felt the best about doing these validation types of integrals rather than doing problems where I'm like, I don't know. I guess the answer is 10.61. Like, I don't know. These make me feel like I'm doing the right thing. Like I know what I'm doing. I feel like these are good confidence boosters for me always. So now that you've had your confidence boosted, let me go ahead and crush your confidence here. All right. So next example here. Gabriel's horn. This is like a super classic example in like geometric calculus here, right? This is a thing that convinces you that you should be a little bit less confident that you really understand how infinity works. We're going to get a weird result for this one right here. What I want to do is two things. I want to know the volume of Gabriel's horn, and I want to know the surface of Gabriel's horn. Gabriel's horn is a shape that is constructed by rotating y equals 1 over x about the x-axis for all values of x greater than or equal to 1. So there is a whole bunch of topics that are kind of converge on us right here. One, we're going to talk about a volume of a revolution of solid. So you need to somehow remember all the way back to the beginning of chapter 6 when we covered that stuff. We're going to talk surface area, which is brand new to today. And you should notice what are our bounds of integration on this guy? Well, it looks like we're starting at 1 and going off to infinity. So it looks like we're going to have an improper integral as we discussed in section 7.8 here, right? So there's actually some chapter 6 stuff, some chapter 7 stuff, and some chapter 8 stuff all littered throughout this problem right here. And what kind of technique do you think we're going to have to do when we're evaluating this integral here? Exactly the one that I've suggested that we should expect. A little bit of some trig sub might be the thing that we see. Wait, are we going to see some? Maybe, ooh. Maybe we'll see some. Maybe I'm getting ahead of myself there. In any event, a lot of topics throughout here. So this is a really good problem. And the result that we're going to get out of this problem is going to make you like, I don't know, you're almost going to be upset about this one when you see it, which is why I like this one so much. So let's go ahead and hit Gabriel's horn right here. So let's see here. So we're talking about taking this function, y equals 1 over x. And I know what that guy looks like. I don't need Desmos' help from that one. We're revolving it around the x-axis right here. We're not starting this guy until it gets to 1, right? That's our starting location for this one right there is x equals 1. But we're interested in taking this area right here and revolving this around the axis right there. So this sort of looks like the bell of a trumpet, but one that goes like infinitely far forever, right? Hey, that wasn't too bad right there. Hey, there we go. This is Gabriel's horn. So the Gabriel's horn is the 3D shape uh, right here, where it's starting at x equals 1 right here and going off to x equals infinity. That sort of trumpet bell shape that we're looking at right there, but it goes infinitely far off, right? So we need two pieces of information. We're interested in the volume and we're interested in the surface area right here. So if we're thinking volume of a surface of revolution, okay, let's see who remembers some things right here. What I like to think to myself is that our disk and washer method is typically the thing that I think to try first. If that ever seems like it's giving me any issues, that's when I think to myself, maybe I should be hitting up the cylindrical shell method instead. All right, that's usually my like order of operations right there. I can admit that I think there's probably some scenarios that the cylindrical shell method is easier, and I go with discs and washers anyway. I probably favor that one a little bit more than I should, but it's okay. I get through these guys. So let's stop and think to ourselves. The thing I'm thinking about this guy right here is that it seems to me like the disc and washer method is actually going to be pretty good since our area is up against the axis of rotation. What this means to me is that when I keep on saying the disc and washer method, this one is just a disc. It's not a washer because we don't have a gap between our region of interest and the axis of rotation. It's butted up against this right here. So if we go to hit up some volume computation right here, then I'm thinking disk washer method. And really, it's not a washer. It's a disc, right? Because here again, our region of interest is butted up against the axis of rotation, so there's not like a gap in between it's going to be a solid object that's right there, right? So what I'm seeing for myself is I know that this is going to be my integral from x equals 1 to x equals infinity of pi times capital R squared times minus pi times little r squared dx, right? We're going to come up with a little piece of a disk for every x value from 1 to infinity. It looks like the radius of one disk, because we're rotating around the x-axis, is going to be the y measurement right here. So it seems to me like the thing that I can kind of conclude from looking geometrically at my picture right here is that capital R is y, which is 1 over x, and lowercase r is just 0 because our inner radius is saying how far is it from the axis of rotation to our region of interest, and it's 0 units always, right? We're up against it right there. So that's, well, when we say that this is a disk and not a washer, what we really mean is lowercase r is 0. I pretty much always just do this as my go-to formula for volume right here, and this covers disk and washer method. The only difference is that if it's a washer, or sorry, if it's a disk, then little r is 0, and that's a washer right there. So it looks like we can go ahead and say that our volume is equal to the integral from 1 to infinity of pi times 1 over x squared dx. Let's go ahead and see if we can integrate this guy right here. So I'm thinking I'm going to pull this pi out front. I'm going to write this as x to the negative 2 dx. I'm going to add 1 to the power, so it becomes negative 1, and I'm going to pop that negative down out front. So I think that's going to be my antiderivative for x to the negative 2, is negative x to the negative 1. We're going to evaluate this guy from x equals 1 to x equals infinity. So maybe now this is all right, all right, all right. I guess if I'm a math professor, I'll write it the right way. You guys harassing me about this all the time. I know, I know. All right, all right, all right, all right. Let me write my pi, since it's really on the outside of everything here, times the limit as b goes to infinity of negative 1 over x evaluated from x equals 1 to x equals b. Okay. There, you happy now? So let's go ahead and do it. Pi times the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. It looks like this is going to be, when I evaluate this limit as b goes to infinity, 1 over b goes to 0. Subtracting a negative 1 is adding 1. So it looks like the volume, and notice this is kind of crazy right here. Gabriel's horn goes infinitely far out on the x-axis right there. But it seems like it only has just a volume of pi, which is kind of crazy, right? Infinite in one dimension, sort of, but a finite volume right there, which is kind of weird right there. But we can handle that that improper integral with the bound of infinity right there without too much difficulty. So there we go. A nice little combination of disk and washer method and our improper integrals, chapter 6, chapter 7 representing. Let's go ahead and hit up our surface area. So I'm thinking that my surface area formula here, we're going to have our integral. Again, I'm thinking that these bounds from 1 to infinity are going to be pretty useful for us. Same situation right here. I'm going to do a dx integral again. Since it's a dx integral, I'm going to write this as 2 pi. Again, I can see that my bands have a radius that is measured in the y direction. If I'm picturing this being a band right here, right, there's my axis. Here's my band of interest right there, right? This has a radius as y. Right. So this is where I'm going to write 2 pi. Y is the direction that I'm measuring my radius in, times the square root of 1 plus dy dx squared dx. Right? So I got my general formula here. Once again, we know that we just need some components for this guy right here. So let's go ahead and find these guys. it looks like we're going to say here that y is 1 over x. We've got that. Therefore, dy dx, we know that the derivative of 1 over x here, that's really x to the negative 1. Taking the derivative, we chop 1 from the power, we're going to get a negative x to the negative 2, also known as negative 1 over x squared right there. So I've got the parts that I need. Let's go ahead and throw them into our surface area formula. And right away, I keep on doing this. Let's get that 2 pi out of there. It's not doing anything for me. Well, I mean, it's going to contribute. Well, all right. I should just stop talking. I keep on saying things that are only true for the next 30 seconds and then are going to change. So here we go. 2 pi times the integral from 1 to infinity of y is 1 over x times the integral of 1 plus. Now I'm squaring dy dx, so you should notice that it's a negative number getting squared, so it's positive. It was 1 over x squared, so we're going to get a 1 over x to the fourth. All right, that is negative 1 over x squared, all squared, is positive 1 over x to the fourth right there. So, I feel uncomfortable now. The reason why I generally feel comfortable with that square root of 1 plus something squared is because I want that something to be squared, and I want it to be something instead of 1 over something. This is making me nervous about our ability to implement like a trig sub or something like that. I'm quite confident that we're not just going to have this whole thing reduced down to like 1 like we did before, and I don't see the trig sub. So my confidence is lightly shaken right now, I'll tell you that. Are we going to be able to evaluate this integral at all? I at least think I could do something like get a common denominator here. And notice that in doing this, 1 plus x to the fourth over x to the fourth. Notice that the one nice thing about getting this common denominator here is that now we have a perfect square on the denominator. So I can take the square root of x to the fourth and get x squared. Further, that x squared down there is times 1 over x, right? So I'm thinking 2 pi times 1 over x times square root of 1 plus x to the fourth over x squared. So what are we getting here? We're looking at, no, remind us where we're at here. Surface area is, that was from 1 to infinity. Integral from 1 to, now I'm dropping things because now I'm just trying to go too fast here. 2 pi integral 1 to infinity of square root of 1 plus x to the fourth over x cubed dx appears to be the surface area of Gabriel's horn. But like, what are we gonna do here, man? I feel a little stuck, and the reason I feel stuck here is the thing that feels almost like something I want to see right now is that I see an x to the fourth and I see an x cubed, and so the stupider part of my brain is like, do a u sub, man, do a u sub. But the reason that's not going to work out is because I need to be picking something like 1 plus x to the fourth to be u. That would give me a 4x cubed to be du. But I'm noticing that we have x cubed in the denominator and dx in the numerator. If this was the reciprocal of this, I could do this problem easily with a u sub, right? That's important. If we were looking at the integral of the reciprocal of this function, u sub would work because we'd have x cubed dx together in the numerator. We'd have 1 plus x to the fourth in the denominator. I could do this u sub if it was the reciprocal. But in this direction, I can't because the dx is separated from the x cubed. One's numerator, one's denominator. I would need them together right there. I don't see a trig sub, right? This isn't 1 plus x squared right there. If I do something like 1 plus sine to the fourth, I don't have a there. I find it highly unlikely that I'm going to find some nice clean trig identities that are going to break down x to the fourths into x squareds, then apply a 1 plus a squared. Like I don't know. I mean, I guess I should try it, but like I don't feel good about this, is what I'm saying. So now I want you to think, well, what did we do? Like we've been in a situation that feels like this already. I know that you guys have just forgotten it because it was slightly uncomfortable. The thing that I'm thinking to myself is that I know that this is a fully continuous function except that x equals 0, and that's not part of our bounds. But our bounds are tending off towards infinity. So what's the suspicion that you might have about the value of this integral? What value might we be getting out? And I think it's reasonable to believe that anytime infinity gets involved as an input, infinity might be involved as an output. Like that's not a that's I don't think it's like something where you should like assume that. That would be a bad assumption. Here's a reason why that's a bad assumption. We got a finite value from an infinite input right there. But like that seems plausible to me. So since I'm recognizing I don't even know what to do with this integral, maybe instead of trying to like compute it, we should take one step back and ask a less specific question. Rather than what is the value of this integral, let's ask a more generic question, which is, does this integral even converge? So let me kind of say some of these thoughts. So back in section 7.8, we introduced a really important idea. It's going to be one of the most used techniques in chapter 11. Is actually a technique that we set up in chapter 7, which is sometimes when you have an integral with an infinity bound in it, that should lead you to say to yourself, maybe the value of this integral is infinity, maybe it's not. That's a more of a classification question, right? What we can do in these cases is we can compare the comparison theorem, right? We can compare this integrand to one that we do know more about. This is an integral I can't deal with. And my question to you is there a very nearby integrand that is something that you do know how to deal with? So here's what I'm thinking. Square root of 1 plus x to the fourth over x cubed. And I'm thinking to myself, this is where your childish discomfort is going to prove mathematically valuable to you. This is where you should start pouting and you should say to yourself, this problem's stupid. I really just wish this problem was blank. And now what you need to do is instead of just being an angry child, you need to actually make an educated guess as to what goes in that blank right there, right? This is, again, I use all of my non-productive emotions to actually push me in the right direction very, very often here. So I'm saying to you, if you were allowed to modify this problem very slightly without meaningfully changing the functions that we're looking at right here, what's a tiny modification you could make to this integrand that would all of a sudden make it something that's very easy for you to manage and something where you can directly, explicitly declare to me what the relationship is between the current integrand and the changed integrand? And here's what I'm thinking. So what I'm thinking to myself here is, man, if that 1 plus just wasn't there, then this is just the same thing as the square as x squared over x cubed. This is almost an easy integral. X squared over x cubed, that's just the integral of 1 over x. I could do that. And in fact, you should remember the answer that we got from that one straight up. That's like an integral that you should just have memorized right here. So here's what I'm seeing for myself, is that this guy right here is a good comparison for us to be making right here. And so therefore, it should be the fact that our integral of square root of 1 plus x to the fourth over x cubed dx from 1 to infinity, this should be greater than the integral from 1 to infinity of square root of x to the fourth over x cubed dx. And notice that the reason that I know this is because this numerator on the left side, our actual numerator, is guaranteed to always be bigger than this numerator over here. The denominators are always the same. Therefore, every single value of x you ever plug into both sides will result in the left side being bigger than the right side. There's one more in the numerator always over here. Square root of it, but still. We're guaranteed larger numerator always over here. Therefore, the area underneath this curve which must be completely above our comparison curve, is going to have more area than this area right here. And what this is really computing, we know, isn't just area, but surface area of a volume of revolution, right? So because this function is above this function, this integral's value is greater than this integral's value. That's the meaningful thing. So now we can ask ourselves, well, what's up with this integral right here on the right? This one I can talk about. Whatever answer I get from the one on the right, I know that the one on the left is even bigger than that. Whoa. All right. So you should recognize that we got back to a very, very important integral that we saw in section 7.8. The integral from 1 to infinity of 1 over x dx. That's our literal first example that we did in 7.8. And then we did 1 over x squared, and we got an answer of 1. Right? Here we get an answer of infinity. There's infinite area underneath 1 over x from 1 to infinity right here. And what we saw by the comparison theorem is that our integral was above that. It must have even more area than 1 over x had underneath it. And 1 over x had infinite area underneath it. Therefore, by the comparison theorem, we can conclude, I'm gonna write a little bit out of order right here. By the comparison theorem, see that Gabriel's horn has infinite surface area. But finite volume. Yes, and I am happy to see one comment in chat basically just says, yep, that's uncomfortable. How weird is this, right? And the answer is very weird. And I know that weirdness is sort of an opinion, except for here it's a fact. It is a fact that this is a very strange type of result right here. That means that if you were to pour liquid inside of Gabriel's horn, you could only fit pi units of liquid. But if you were to try and paint Gabriel's horn, it would require an infinite amount of paint. And so, once again, I should say to you, the whole point, in a sense, of calculus, well, okay, it depends on kind of who you ask right here, but the point of calculus originally was to be able to do physics problems. But now what we really have learned is that the underlying theme of calculus is, how the heck does infinity work? What does it mean for 2 points to get infinitely close together to compute slope? What does it mean to compute the area of a rectangle that's infinitely thin? What does it mean to add up an infinite number of short arc lengths together that are straight lines to imitate a curve? What does it mean to blah, blah, blah? And every single one of these questions that we ask is saying, what's up with infinity, really? So, in one sense, it should seem like by taking more and more calculus, you're going to get more and more confident with what infinity is doing. This problem does not make me feel better about what infinity is doing. I like to think that I feel it out and that I get it, but right here, this is incredibly strange. And so, as I said, this Gabriel's horn example is a very classic example when you're learning about things like surface area with integration, because it brings us to a result that we can find the volume easy, and we can find that the surface area diverges easy, and neither of these were directly easy, but if you put all the parts together, that wasn't too bad right there. But a difficult result to like grapple with. I mean, this is I've always grown up just hating it when teachers or professors use the words like, "I want you to grapple with this material," and I'm like, I've always just kind of hated those kind of like frou-frou phrasings right there. I feel like I'm in a boxing match with this answer right now. I feel the grappling straight up right now. How is this possible for us to have pi volume and infinite surface area right here? It feels uncomfortable right here. But that being said, I feel super confident in my ability to evaluate volumes, and I feel super confident in my ability to evaluate surface areas in my use of the comparison theorem right here. I know for a fact that this integral that we considered actually right here is completely the curve was completely below our curve of interest. I know that this integral is even smaller than this one, and this one diverged. This one's bigger than it, so it must have also diverged by the comparison theorem, but that's a pretty tough one right there, right? So we're able to do this one, but this is just one of those things to say, I think that the more you learn, what often ends up happening for lots of people, and this is like a well-studied psychology thing, present in modern day politics, which is that when you are uneducated about a topic, it's easy for you to think that you know a lot about it because you don't know how much there is to know. The more and more you learn about a topic, the more that you feel like you don't know anything about it because you're more aware of how much there is to know. I think that that's kind of like a healthy thing of saying, like, don't be overconfident in how well you understand things. This is a kind of crazy result right here. And I think this is good to make sure that you aren't like, I hope that after seeing this, that none of you would ever go out into the world and be like, oh yeah, I understand how to deal with infinity. Because, like, do you really? Because I'd say that this problem says, ugh, right? So, all of chapter 11, I want to just tell you guys, is more about this idea of what does it really mean to like add up an infinite number of objects? Is that even like a well-defined operation right there? Do we really even get sensible values out from it? Does it make like, can we interpret this in any meaningful way? So just know that like a huge chunk of all of calculus for however much you end up taking is always going to be like, what's really going on with our interactions with infinity, because it's uncomfortable, and it sort of remains uncomfortable for kind of for infinite amount of time right there. Okay, I had to throw in one infinity joke right there. But so there we go. So we found our volume and surface area for Gabriel's horn, and it's a little bit weird right there, but a really cool result that we can kind of arrive at, and a really nice culmination of all the things we've seen. I mean, we saw like 6 different sections just showed up out here, right? We got basic integration, bounds at infinity, comparison theorem, disk and washer method right here. We had some geometry that we had to be able to interpret. All these kind of good things out here. So good stuff in this problem right here. It's got a lot of great parts, and it's got a very surprising result that's difficult to wrap your head around, I think, right here. So if that didn't make you uncomfortable enough, I'd now like to make you feel slightly better about some things as our conclusion to today right now. Show you a little, and again, there's no magic tricks in math. But this is gonna all to me. The first time I saw this, I just walked around. I got like a sinus infection after the first time that I saw this, because I just walked around with my mouth open for like 2 days and I got all dried out in there. So I'm going to attempt to impart that same thing on all of you here today. So let's feel a little bit better about math right now, as opposed to the feeling a little bit uncomfortable about math like we just did right here. So we started this today by looking at the formula for the surface area of a sphere. How is that tied to the volume of a sphere? And what I want to suggest to you is that there's some really, really close, deep relationships between this volume and surface area stuff right here that is really representative of one of like the broadest themes that I could possibly come up with. That's saying, if somebody just says to me, "Hey Tony, man, what's up with integrals and derivatives?" If somebody asked me that like kind of lame and massive question right there, this is, I think, what I would tell them. I think that this would be my answer to the question, what's up with integrals and derivatives? This is my answer right here. So let's do some geometry that's going to make you feel good. All right. So what we're going to do is we're going to start doing some geometry with the easiest shape that there is in geometry, a circle, right? And typically the way that we measure circles is we start at the middle and we measure them with a radius. That's the most common way to define what a circle is. The definition of a circle, it is all points that are equidistant from some central point. All right, and there we go. So we're measuring distance from a central point. We're labeling it r. That's the definition of what a circle is. What you know is that this has an area of pi r squared. So what I'm going to do right now is I'm going to go ahead and just blindly do a little bit of calculus here, and I'm going to take a derivative. And what we're going to notice here is that when we take the derivative of area with respect to our central measurement right there of r, is we're going to get 2 pi r, and oh my gosh, do you know what that is? I don't want an error right there. Well, that's kind of interesting, isn't it? Is it not interesting to you that we get circumference is the derivative of area? I can't draw. I'm getting too excited that I can't write. Circumference. That's pretty interesting, right? But then you should definitely be saying to me things like, yeah, but Tony, I mean, okay, so you did some cool tricks with a circle right there. No math tricks are valid when it's circles. And 2 dimensions, that's just cheating. So maybe we ask ourselves, can we make this problem more interesting by A, maybe not using a circle, or B, maybe not being in 2 dimensions? Okay, so let's talk about the volume of a sphere instead. Spheres, just like circles, are often measured exclusively with the radius measurement right here. Sphere definition, same as the circle definition, except it's just in 3 dimensions. In 3 dimensions, it's the set of all equidistant points from a central point right there. The volume of a sphere was something that we computed back in chapter 6, and we got our 4/3 pi r cubed. And notice that if we take a derivative of the volume of a sphere with respect to its central measurement, what are we getting? Well, oh my gosh, we're getting 4 pi r squared. That's the surface area. Well, that's weird again, right? But now again, you should say, well, okay, to like this just looks like cheap parlor tricks right here. It's like, oh, cool features of the most nice shape in the history of shapes right here. Okay. Fine. Let's see if this type of relationship where the inner parts, area and volume, have a derivative of outer parts, perimeter, right? Circumference, surface area. It seems like we're taking the derivative of what's on the inside and we're getting what's on the outside. But again, uh, nothing in math should be trusted because it worked with a circle or a sphere. It's the nicest shape that there is. So let's see if this keeps going if we pick a less nice shape. Let's do this with a square. So we tip. Wow. Okay, that was embarrassing. Let's fix that line. Hey, there we go. The one straight line survived. All right. Let's see if I can draw something that doesn't have 4 jagged lines here. Closer. All right. Here's my square. What we know is that we typically measure a square by its side length, right? If I said to you a square of side length 3, that's the great descriptor of a square that we typically use, right? So in this case, our area is x squared, and we take a derivative. And what are we expecting to get for our derivative right now, right? What we've seen from our previous 2 examples is if there's any special relationship here going on at all, then the derivative of area should be giving us perimeter, right? We got circumference in the previous one. Circumference, that is perimeter, right? It's just a special word for perimeter. If I take my derivative here, dA dx, well, here I'm going to get 2x. And notice that that isn't equal to the perimeter. Our perimeter here is 4x. Why didn't this work? Why did that not work? Well, we changed the way that we did our measurement here, right? Notice in the previous 2 examples, we measured from the center of the object. Here we measured around the boundary of the object. Let's try the square again. But this time, let's form a central measurement here. So now I'm going to call that length x right there. In this case, it appears that one side length is now 2x. And therefore, our area should be 4x squared, based on this style of measurement right here, measuring from the center to the edge. Now, if I go ahead and take a derivative, dA dx is equal to 8x. And that is the perimeter of this object. So now I feel good. Now I feel like there's this special thing about measuring from the center. But now also you should kind of be saying to yourself, all right, that was pretty cool. You should all be at the pretty cool area right now. But now you should again be saying to me, because if you're a good academic, then that means that you're infinitely skeptical and that this is just a trick, right? And again, you should be saying to yourself, so sure, you stepped away from the nicest shape in human history of a circle into a square, which is arguably the second nicest shape in the universe, right? Maybe we could do something a little bit even less comfortable than this. And let's ask ourselves what would come next right here, something else that we could try. Well, what if we did this with a rectangle? Well, I learned my lesson from the last two examples, which is that, and I'm going to kind of put my label these guys as the good versions and the bad versions of this one right here. I learned my lesson, and the lesson from the last two examples was measure from the middle if you would like to see this relationship emerge right here. But notice the uncomfortable thing about using the rectangle right here is that when I go to measure from the middle, I can't define this in terms of one variable. Notice that the important thing here is that circles and squares are really two of the essential shapes that we can measure with a single one parameter. Most other shapes require multiple measurements for us to be able to define things like their area, right? So in this case, since that's an x label or x dimension, I'm going to measure that as x, and this is a y dimension, so I'll call that value y right there. And so now we want to know things like what's the area and what do we expect to get for the derivative. But we're going to come up to an issue now, which is that because of the fact that you're all in this class right now, that means that none of you have taken Calc 3 yet. And Calc 3 is where we do multivariable calculus. And so what we can do right now is we can see what we're going to define the derivative to be in multivariable calculus just by thinking about the relationships that we're seeing on this page right here. So what I'm seeing here is that this is 2x. I can see that this right here is 2y. I can see that my area here is 4xy, right? But how? How do you take the derivative of a? There's two variables. But the cool thing is that you know what answer we should be getting because you've seen this pattern emerge now. Sorry, I'm writing crazy words not in order right now because I'm a crazy person. So the point here is that you don't know how to take the derivative of the a function because what does it mean? The derivative with respect to x, the derivative with respect to y? Why would we pick one of those or the other, right? That doesn't really make sense. Just be like, oh, I'll just do it with one of them. I mean, there's two variables that are sort of equally important to us here, x and y. It's not like just pick one. I can't really define one in terms of the other here. I have no defined relationship between x and y. So, however the derivative works, the perimeter is P equals what? 2x, 2x, 2y, 2y? It looks like it should be 4x plus 4y. So, what must be the multivariable derivative rule. So I'm asking you to tell me, what are you going to show is the appropriate way to take a multivariable derivative next semester? That's the question that I'm asking you right now. And the thing that you can see is we're starting with 4xy, and we know, based on the relationship that we built on this page right here, that the derivative of area and volume should be giving you the skin of the object in however many dimensions that is, perimeter or surface area right here, right? We measured from the center like we learned that we should do in the square example here. So what do you think should be our rule right here? Well, we will define this thing in Calc 3 to be, right? And I'm going to say here, the derivative of area with respect to what? That's really the question right there. All right, that should be a question mark. I wrote it really small. I'm going to make it a little clearer right here. Well, we're going to write this a little bit different of a way in multivariable calculus because we don't really directly have a way for us to just state a single variable right there. So what you're going to end up learning next semester in Calc 3 is that we're going to refer to this as the gradient of A with the little upside down triangle right there. And what this is going to be is the partial derivative of A with respect to x plus the partial derivative of A with respect to y. Now, there are some technicalities to this that I'm skipping over right now just for the sake of this geometry situation right here. It turns out that there's actually going to be some vector components that are also involved with this right here. There's going to be an I on the first term, a j on the second term, and you need to know what a partial derivative is, which is what you're going to get to next semester. But the partial derivative idea is very easy. When I say the partial derivative of A with respect to x, that means assume all other variables are constants just for the purpose of this derivative. So that would be like saying pretend y is a constant and take the derivative of 4xy with respect to x. Well, that should be giving us 4y. Take the derivative of a with respect to y, assuming x is a constant, then it's just like 4x times y. Take the derivative of that, you just are left with 4x right there. So with this, we can sort of backwards intuit what must be the multivariable derivative rule simply by knowing the relationship between area and perimeter of a rectangle. Oh yeah. Ooh, that's some good stuff right there. So this is a sweet idea right here. This is like my little parlor tricks for geometry right here, is to show this really broad theme right here. So I want to say the big picture of what we just saw right here, aside from the fact that we all just learned a pretty important Calc 3 idea by just looking at the derivative of dimensions of a rectangle. Oh yeah, oh that's nice right there. So here's our really huge idea. What derivatives are really doing is they are taking in information about something that is contained. And when you apply the derivative, what it's going to spit out is information about the container, the edge, right? What was contained was the area. The container of that area is the circumference. It's the edge, it's the skin of the disk. We took in the containment information. What was contained was the volume of the sphere. When we took the derivative, what it told us was, what does the container look like? What does the skin of the sphere look like? We got its surface area. It even worked for rectangles and for squares, as long as we measure from the center, which is an interesting idea right there. You guys already know that that direction goes the other direction, right? Now, when we integrate things, what are all the pieces of information that you need for an integral? You know that when we integrate things, the picture that we draw is that we have some curve out there. We have an A, we have a B. Well, holy cow, what are all the pieces of information that we take in? We say the area underneath the curve down to the x-axis between A and B. Well, integrals take in all edge information. And they tell you what's contained inside. Derivatives take in all contained information. So this is sort of like an inside-outside relationship with derivatives and integrals. One will take in the outside and tell you what the inside looks like. One will take in the inside and tell you what the outside is going to look like right here. And I think that's a really, really nice geometric idea to kind of hold as to what integrals and derivatives are doing right here. Integrals take in literally in 2 dimensions. It needs the 4 pieces of information, top, bottom, left, and right, or you can't do the problem, right? It's a four, we know how it's bounded, and we'll find out what's inside. But we just learned that derivatives are going to do the inverse of that, and we know to expect derivatives to be the inverses of integrals. But I don't think we kind of like broadly see this direct relationship that if you ever know an area or volume formula ever, you can always just take its derivative to find perimeter or surface area information. And this applies to context well beyond just 2 and 3 dimensional geometry right here. So I think it's good to think about containers, the object on the outside, versus what's contained, the object on the inside right here, and recognizing that those are always going to have a derivative or integral relationship right here. As my last thought with these guys right here, I also like to think about this. When we say what's dVdr, what is that really defining? Well, this dV is the change in volume, and this dr is a change in radius. So what this is really saying is this. The volume of a sphere is whatever the formula is. I'm asking you, how does the volume of a sphere change, that's dV, with respect to an infinitely small change in radius? Well, how it should change is you should just paint another surface area over it, right? You should picture this as being like paper mache over a balloon, right? Each layer of paper mache is infinitely thin. It's just wet newspaper, right? But how much did you just apply in volume? One surface area is worth around it, right? You just covered the whole thing in one surface area. It's an infinitely thin layer, right? So surface area and perimeter are how the actual area or volume change when you change that inner measurement dimension by an infinitely small incremental amount. You're not accumulating like a thick shell of it because it was an infinitely thin amount. It's really more just like you're applying a layer of paint to the outside of it. And what we know is that technically paint has thickness, but it's not like you think to yourself, oh, I'm going to paint my walls, my room is about to get smaller. You don't really think that to yourself. It's very, very, very technically true, but it's such a small change out there that we don't ever think of it that way. So recognize that when we take the derivative of a volume or an area, it makes a ton of sense that we got the skin of the object, because it's like saying, well, how much would the volume or area change if we change the radius by an infinitely small amount? Well, that would just be like adding another coat of paint onto the outside, and it should change you by exactly one surface area's worth of volume. I hope that feels really good to you for our kind of conclusion for our geometry topics in here. I feel like, it's not like calculus is all about doing geometry necessarily. It's used for so many other purposes. But these are the types of relationships that help me feel really good about when I take derivatives and integrals off in your guys' future classes out there. This is the stuff that makes me feel like I really understand what's happening underneath the hood when I think about derivatives and integrals. So I hope that you appreciate my math parlor tricks here, and particularly the fact that we just arrived at some Calc 3 conclusions today again by looking at a simple idea of area and perimeter of a rectangle led me to probably the most key statements in Calc 3 that you're going to come up with right here. I'll just say my last thing right here, gradient of A. So very cool right here. I really like this when I was shown this by one of my professors. Well, he was my professor in undergrad, but he showed it to me when I was teaching at my undergrad years later. And as I said, I felt pretty cool once I saw this out here. So this is our conclusion to geometry in this class, essentially right here. So again, I'm not going to be making any videos for a few weeks right now. We've got spring break next week. We got baby week after that. And I'm going to see you guys the last week of March again for applications to physics and engineering. Absolutely hit me up with questions that you guys have about anything as usual. I'm going to be getting things graded so that all of you guys have your homework returned to you and graded with keys available before that midterm occurs. Remember that I'm going to send you a message first about when you should expect the midterm to be available and what the available time is, and like when is it going to become available and when is it due. I'll send you a message before the fact that when I've decided what those dates and times will look like. Then I'll post it in Canvas in like a week 9 module. It'll be like the only thing in the module will just be like your midterm is right here. So keep an eye out on Canvas. Don't miss that or anything. It's going to be middle of the week. This is going to be me saying you have from Wednesday to Friday or Tuesday to Thursday or Tuesday to Friday or something like that to do it. So don't miss that. And I will see you guys in a few weeks here. I'm sad that I won't be making a video for a while, but I'll see you guys with applications to physics and engineering. We're going to look at moments, center of mass, some cool stuff like that of irregularly shaped objects. Pretty cool section here in 8.3. And then we get to hit 8.5, which is probability. One of my favorite sections in this class. I wish that we got to spend an entire semester on calculus-based probability. Unfortunately, it gets relegated to exclusively one section, one day. But really cool stuff in the probability section. I'm gonna shake my fist at a lot of you guys to take a whole nother class based on what we're gonna cover in 8.5. So I really look forward to that one as well. So I will see you guys for 8.3 and 8.5 in week 10, which is the last week of March. Have a good one, everybody. I will see you guys then.